So the first part of this just says determine the non-permissible values. Now whenever a question is asking for non-permissible values, they're trying to find out what are the values that are not allowed. And in math, we've learned a couple of things that are not allowed. We're not allowed to divide by 0. We're not allowed to take the square root of a negative. We've seen we can't have sine and cos bigger than 1. So we start to get a collection of things that aren't allowed in math. And in this case, looking at the question, the only thing I see is dividing. And so we're going to look through this and find out where are we dividing, and where we're dividing, what would the non-permissible values be. So for part A, we've got cotangent and cosecant equals cos. Within that, we've got identities that we could use. So we have our quotient identities. We could change cotangent to cos over sine. And as soon as we change cotangent to cos over sine on, here's the left side, then we see that we're dividing by sine. And so we have to figure out where would that equal 0, because that'll be bad. And on the bottom we have cosecant, and cosecant is 1 over sine. On the right side we have cos theta. And now looking at this, we have to find out, well, where could I possibly divide by 0? What would be my non-permissible values? Well, I'm dividing by 0, could divide by 0 here, because I'm dividing there. I'm also dividing here. So what can't happen in this question? We can't have sine theta equal to 0. Because if sine theta is equal to 0, then we'll have dividing by 0, and we'll have a bunch of non-permissible values. So then this question is really asking, can you tell me all the values where sine theta is equal to 0? Well, we would have, from our unit circle, 0, pi, 2 pi. That would be the first time around. We'd also have 3 pi, 4 pi, 5 pi, 6 pi, all of those all the way around. Maybe you remember how to write all the zeros of sine, but they're all the multiples of pi. So we would write that as k pi. So when we're looking for non-permissible values, all we're looking for is where are we dividing by 0? And then you're going to have to write the general solution for that, that theta can't equal, oh, I should put that a little bit nicer in green. Theta can't equal k pi. So for the second one, before we prove them, we'll do the non-permissible values for both of those. On the left side of my equation, I have cos of theta. On the right side of theta, I have 1 plus cos over 1 plus secant, and I'm going to change that secant to 1 over cos. Do we have any places that we're dividing? Yes. What can't equal 0? Cos theta can't equal 0. So we'll do that first. Cos theta can't equal 0. Now if we think about our unit circle of where cos theta is equal to 0, that's at pi over 2, 3 pi over 2, 5 pi over 2. Sort of two ways that we can write that. If you remember, because it's going to be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. All odd numbers times by pi over 2. So if we are going to write that in one way, you can make an odd number by going 2k plus 1 and multiply it by pi over 2. Or, if we think about our cos graph, and we think about here's pi over 2, here's 3 pi over 2, here would be 5 pi over 2, here would be 7 pi over 2. How much is it a jump in between these? It's only a difference of pi. So another way of writing these non-permissible values is you could say, start with one of the ones that you know. So I'm going to start with this one right here, pi over 2. And then I could add or subtract pi as many times as I wanted. And you get k as an integer. So those are two ways to write that same thing. You could choose whichever one makes the most sense for you. Maybe the odd number makes sense for you. Maybe you like to see it on the graph and see that there's a jump of pi in between those points, and then just add k pi as an idea. Okay? Is that the only place? So we did this one. Is that the only place we're dividing in this question? No, where else are we dividing? On the whole bottom. So we also have to solve this, that this whole bottom, 1 plus 1 over cos theta, can't equal 0. How do we solve that? Well, if I was solving for that for equaling 0, whenever you have a fraction, how do you get rid of the fraction? Multiply. So if we were solving that equation, you multiplied everything by cos, you would get cos theta. And cos theta times 1 over cos will be plus 1. That can't equal 0. So that means that cos of theta can't equal negative 1. Is that on our pi plate? What angle? Can't equal pi. That would be one of them. What would the next one be? 3 pi, 5 pi, 7 pi. So here, you could say those are all odd numbers times pi. So we could write it as theta can't equal if we notice that they're all the odd numbers times pi, we could write it this way. If we think about it on the graph, I'll do it on this same graph in red. Can you see that negative 1 is right here at pi? And that the next time it's negative 1 is here. How much of a jump is it between those? It's a jump of 2 pi this time. So another way of writing this, you could say theta can't equal pi plus as many multiples of 2 pi as we want. So those are our non-permissible values. We have to look everywhere where we're dividing in the question and then solve those equations. So for looking for non-permissible values, it's like a solving equation where we're solving the general solution. Often on the exam, what they'll ask is, can you tell me one non-permissible value for this? Or can you tell me two non-permissible values for this? Or they might just say, tell me the non-permissible values between 0 and 2 pi. But it is possible that they could say list all the non-permissible values, and then it becomes like a general solution question. So that's part I for both of those. For the proofs, I'm going to give you scrap paper. You're going to do the proofs on your scrap paper. I'm going to come around and steal different proofs as you're going and take pictures of them to put up on the screen so we can discuss them after. So part A, here are a couple of examples. Here, perfect, wrote out the question, great to draw the line to separate the left side and the right side. And here, we've changed cotangent to cos over sine, cosecant to 1 over sine. We've got a fraction divided by a fraction, so we multiply by the reciprocal, the signs will cancel out, and we'll get cos. Couple things that I want to point out on this one that I really like. Okay, first of all, there is good use of space. I like how there is space in between each of the steps, so you can really see that this whole thing followed from this, and then this followed from that. And that spacing in there helps you see, because one thing you always want to check is what I write next, is it equal to what was above it? And if it's equal to what's above it, then I'm doing things right. Anytime that you have a step where you only do a part of it, okay, you're going to lose a half a mark because your next step wasn't equal to what's above. So you need to make sure that each step is equal to above, and this does really well. What I also like about this one is when they had the fraction over the fraction, this middle line is a little bit wider so that we can really tell what's on the top of the fraction, what's on the bottom. So there is a proof, worked out perfectly, good formatting. Here's another one, changed right away. This one didn't write out the question to start with, so already on the exam, they would take off a mark because you made it equal after you started, okay? And you are saying that the proof is equal before you've proved it. You're allowed to write out the question with the equal sign, but then if you make anything equal before you prove it, it's a 1 mark deduction. So we want to write out the original equation with the line. And then it is true that these signs will cancel out, but I'm not sure, and the person who might be marking this on the final exam might not be sure that you really understand why those can cancel. Like if you have 3/5 divided by 2/5, does it make sense that those 5s can cancel out? It's better, it works, but it's better to show that you're multiplying by the reciprocal, and it's because there's a 5 on the top and the bottom that they cancel out. Because you might be tempted sometime by canceling out early like that, you might accidentally cancel something that can't simplify, and then you're going to run into problems. So for this one, even though this works, I would take the extra step here, show the multiplying by the reciprocal, and then go from there. Here's another one with part A. I would avoid that equal sign in between, because again, if you make a proof equal before you're done, there's a deduction for that. So the marker might say, does the person here think that these two are equal before they are? So it's just safer to just draw the line down the middle, work on one side. I really like the box around the final answer here to show that yes, this is the same as this side, and then you just need your left side equals right side. What's nice about doing proofs this way is you can see those little things that you can make mistakes on, or those little formatting things that can help you out. Whereas when I do them, I'm not making any, well, I'm trying not to make any formatting mistakes as I go. And then it's hard to see, oh, I didn't know that that would be a deduction. Oh, this is part B? So here we've got 1 plus cos theta over 1 plus secant theta. Again, we didn't write out the original equation here. We did a little bit of a change, so that might be a deduction. Sometimes on the marker thing, they would let that go. Generally on your final exam, the way the formatting is on your final exam is they draw the line for you, and you have the question already written out, so you don't have to rewrite it. So these kind of mistakes wouldn't happen on a final exam, but when you're writing things out that way, they do a little bit. Now, this is a strategy. What we see in this question here and what the person has done is a strategy that you will use over and over and over again. And it's something we did at the beginning of the unit, was just working with fractions. That main strategy is if you've got fractions inside of fractions, or if you've got two things that aren't a single fraction, use your skills with fractions to write it as a single fraction. So what do I have here? I have a fraction inside of a fraction. How do I write that as a single fraction? Well, if you can get a single fraction in the top of your denominator and a single fraction in the bottom of your denominator, then you'll be able to multiply by the reciprocal and get a single fraction in the end. And about 90% of proofs, if you can write both sides as a single fraction, you'll be done. 90% of proofs are that easy. Just write things as a single fraction. We will look at the other 10% that come up and look at strategies for that, but that's coming up. But for right now, can we write things as a single fraction? So this person got a common denominator because they needed to add 1 plus 1 over cos theta. Got a common denominator on the bottom. That gave this single fraction on the bottom. Again, one thing I would learn from the other proof from before, I might have made this line a little bit longer just so that I remember that this is on the bottom. Because what sometimes happens is people cancel these out and then they just leave cos on the bottom. And in the end, cos needs to be on the top. So that's a little formatting thing here. Now, another thing that some people get confused about, the 1 plus cos theta on the top, that is a single fraction. You can write that all over 1. So we have 1 plus cos theta over 1 multiplied by the reciprocals. The 1 plus cos theta cancels out, and we just get cos theta. Perfect. So this is a great strategy for this one. Here's another example. Here's one where someone got stuck. Okay? And I wanted to point out, where did the person get stuck on this one? They did a good first start. They've got the line drawn. They changed secant to 1 over cos. And now they know that when they're dividing by a fraction, they multiply by the reciprocal. And so they're trying that here to multiply by the reciprocal, but they didn't get a single fraction on the bottom first. So that idea of getting a single fraction on the bottom of your fraction, a single fraction on the top of your fraction, and then multiplying it would have worked. But not doing that first and trying to multiply it through, you see that at this point they're stuck. They're like, I don't know what I need to do from here because it's not going to match up. Here's another example where the line hasn't been drawn. Okay? So it looks like you're equating something before you've proven it. If the line was drawn like this, it would through the equal signs, it still appears to be equating. If the line was drawn like this with the equal signs on the other side, then it would be assumed that this equal sign just meant from above, and then that's okay. So see that really format-wise, we're finicky on not equating something before we're done because we're trying to prove it. Again, here we're having issues from this step to this step because we didn't get a single fraction on the bottom first so we can multiply by the reciprocal. And in this example, this is an example where they are equal and then the person is moving something from one side of the equation to the other. So the reason we draw the line is because one of the main things in a proof is you're not allowed to move from one side of the equation to the other. So here, the fact that this got moved to the other side of the equation, they multiplied both sides by that. They get something that's equal, but for this proof, there would be you would have to, I don't know if it would get 1 mark or if it wouldn't. You would lose some marks because you're working from one side of the equation to another. So on a proof, you're not allowed to do that. I'm going to show you someone in the other class came up with this proof. So this is another way of doing it. And this is one of the reasons that I like to give you the chance to do the proofs and put them up here, because we get so many different ways of doing it. And as long as your next step is equal to the step above, there's nothing wrong with that. And we will have some proofs later that one method will take a page and a half and another method will take 2 lines. So they're both right, but you also might over time say, I want to know how to do those shorter ways, how to see a different technique. So in this one, the person started the same way. 1 plus cos theta on the top? Thank you. There we go. Yeah, it's very hard to prove something that's not provable. If you write down the question wrong to begin with, it's going to be a long proof. So what the person did in this one is said, if I move from one step to the next and I multiply by 1, I'm not going to change what it's equal to. And I have a problem here in that I have a fraction in the bottom, and I don't want that fraction. So if I multiplied the whole bottom by cos, that would get rid of that fraction on the bottom. But if I do that, it's no longer equal. If I multiply the top by cos as well, then what I'm multiplying that fraction by is cos over cos, and that blue is equal to 1. And if you multiply by 1, it doesn't change what it's equal to. So on the top, they got cos theta plus cos squared of theta. On the bottom, when you distribute the cos, they get cos of theta plus 1. Those aren't the same, but can we simplify? And one of the key strategies for simplifying that you always look for is, can you factor? Well, on the top, we could factor out a cos. In fact, if we hadn't multiplied out the top, it would already be factored. It's just cos of theta times 1 plus cos of theta. And we have the cos of theta plus 1 on the bottom. Those would simplify. And we're done. So just showing you a different strategy that also works out. Although this strategy works out, I still would highly recommend you get really good at, can I make a single fraction on the top? Can I make a single fraction on the bottom? And if I can do that, multiply by the reciprocal and simplify, you're going to find so many questions you're going to be able to solve that way. Okay, so I'm going to give you some time to try some proofs in the homework. 4, 8II, 9II, and 11.